In our discussions of acids and bases so far, we have taken a look into some different definitions. We've talked about Arrhenius acids and bases, and we've talked about Bronsted-Lowry acids and bases. Now, the next thing we're going to talk about are something called conjugate acid-base pairs. Acid-base reactions of our Bronsted-Lowry acids and bases always involve the transfer of protons, or our hydrogens. So remember, we defined the acid as being the proton donor. We define the base as being the proton acceptor. Because many of these reactions are reversible, the products formed can transfer protons to reform our original substances. This gives rise to what we call conjugate acid-base pairs. So we can look at the example of ammonia, NH3. So when we put that NH3 into water, we're going to produce ammonium cations and hydroxide. Now our NH3 goes from being NH3 to NH4 plus, so we can follow our line here. So we go from NH3 to NH4 plus. And so during that process, the number of hydrogens has increased, indicating that that NH3 accepts the proton. The water goes from H2O, where we have 2 hydrogens, to OH minus, where we have 1 hydrogen. Here, the number of hydrogens decreased, so that water is behaving as an acid. It donates the hydrogen. But we've got our reversible arrows here, so this is a reversible process. The hydroxide can interact with the ammonium cations, reversing the reaction. It can reform the NH3 and the water. During this process, that NH4, or what's happening is that NH4 plus transfers a proton to the hydroxide. So during that process, we go from NH4 plus to NH3, the hydrogens decrease. So that NH4 donates our hydrogens. And so if it's donating the hydrogens, it's behaving as an acid. At the same time, my hydroxide goes from OH minus to H2O. The number of hydrogens increased. So that means the hydroxide accepts hydrogens. And so that hydroxide is behaving as a base. So we get these pairs. We've got acids and bases in the reactant side. We've got acids and bases in our product side. What shows up on our product side, we're going to refer to those as being our conjugates. So every acid that we start with has a corresponding conjugate base. Every base has a corresponding conjugate acid. So if we're going to compare a base to its conjugate acid, we're asked how does the number of hydrogen differ? So we're comparing NH3 to NH4 plus. I have 3 hydrogens, and then I have 4 hydrogens. The original base, we're going to find, has 1 less hydrogen than its corresponding conjugate. So the original base will always have 1 less hydrogen than its corresponding conjugate acid. Now, if we compare an acid to its conjugate base, so we're going to compare water to hydroxide. The water has 2 hydrogens, the hydroxide has 1. The original acid has 1 more hydrogen than that conjugate base. So what we're going to find is that our acids and bases differ from their conjugates by a single hydrogen. The base always has 1 less hydrogen than the conjugate acid. The acid always has 1 more hydrogen than the conjugate base. So it's going to be important that we are able to identify conjugate acids and bases. So here in problem 11, we are given some pairs. We're assuming that each of these pairs has arisen from a proton transfer. And so we want to identify each as being an acid and its conjugate base, or a base and its conjugate acid. So we're assuming the first thing listed, that's going to be what appears on our reactant side, and it's either an acid or a base. The second thing listed is what appears on the product side. So it's going to be the conjugate acid or the conjugate base. So if I look at comparing to water and hydroxide, H2O goes to OH. We lose a hydrogen. So that means my H2O has got to donate a hydrogen to something in order to form that hydroxide. So that H2O is an acid. If that's the acid, that means the hydroxide is the corresponding conjugate base. It's a base because if we reverse that reaction and we go from OH to H2O, we have to gain a hydrogen. So when water is behaving as an acid, hydroxide is its conjugate base. Now in B, I've also got water again, but this time it's paired with hydronium. So again, I'm looking at what happens to my hydrogen. I start with 2 hydrogen, I end with 3 hydrogen. So we are gaining hydrogen. If we're gaining hydrogen, that means that water is behaving as a base. And if water is a base, the hydronium is its corresponding conjugate acid. And again, it's an acid because when we go from hydronium to water, we've got to donate a hydrogen to drop down to 2 hydrogens. Now next we've got HCl and Cl minus. We go with 1 hydrogen to no hydrogens. That means we are donating. So HCl is an acid. The Cl minus is its conjugate base. Then we've got CO3 2 minus, so we've got carbonate. And then we have HCO3 minus, so bicarbonate. I go from 0 hydrogens to 1 hydrogen, so we are gaining a hydrogen. So that carbonate has to accept hydrogens, making it a base. The HCO3 minus is then the corresponding conjugate acid. It's a conjugate acid because to reform that that CO3 2 minus, we've got to donate a hydrogen. And then finally, we've got HCO3 minus, so again, bicarbonate, and then I have H2CO3. We go from 1 hydrogen to 2 hydrogens. We are gaining. So the HCO3 minus is a base here. It's accepting a hydrogen to form the H2CO3. That means the H2CO3 will be the corresponding conjugate acid. Now, we're then asked if the bicarbonate, the HCO3 minus, is amphoteric. So remember that we said that amphoteric was going to be a substance that could behave as both an acid and a base. Now, if we look back at our previous problem, in part D, that HCO3 minus was an acid. But in part E, it was a base. So we have scenarios where it can behave as both an acid and a base. So that HCO3 minus is going to be amphoteric. So again, we know it's amphoteric because it behaves as both an acid and a base. So in addition to being able to identify conjugate acid-base pairs, we need to be able to write proton transfer equations, so showing that acid or base transferring its hydrogens. So for the following set of substances, we're told these are all Bronsted-Lowry acids. So if we've identified something as an acid, that means it is donating hydrogens. So we need to write the formula for the corresponding conjugate base. For donating a hydrogen, we are removing and H plus from the compound. That impacts our charge. When we are writing the formula, we've got to take one hydrogen away and we got to take one charge away in order to get our new formula. So if my HSO4 minus is an acid, it's going to donate hydrogen, so we're going to lose that hydrogen there. So its conjugate base has one less hydrogen, so we get SO4. Now we need to know the charge. The original charge was -1. We removed a hydrogen, so we subtracted a hydrogen. We need to subtract a charge. We removed one hydrogen, we remove one charge. So -1 minus 1 is going to be -2. So the charge on my ion here is 2 minus. So if HSO4 minus is my acid, SO4 2 minus is its conjugate base. Then we've got a CH3 NH3 plus. Again, we've already said that these are acids, so it's going to donate a hydrogen. When we go to take a hydrogen off here, it matters where we remove the hydrogen from. So I've got the CH3 here, and I've got the NH3. So again, it matters where we take the hydrogens off. Our acidic hydrogens have to be polar. Remember that the CH3, those are non-polar hydrogens. If they're non-polar, they are not acidic. They cannot be donated. My bonds to nitrogen, though, are polar. If they're acidic, those are the hydrogens that we're going to lose. So we cannot take the hydrogens off of the carbon. If we do so, that is incorrect. The hydrogens are coming off of the nitrogen. So I go from an NH3 plus to an NH2. In terms of my charge, I started with a +1. We take one hydrogen away, so we take one away from the charge, leaving me with 0 charge. So my formula is CH3 and H2. And then finally, HF, we take the hydrogen off, it becomes F minus. So in this scenario, we were told they are all acids. We take one hydrogen away from the formula, we take one away from the charge, and that gives us the formulas for our conjugate bases. Now, in problem 14, these substances we're told are all Bronsted-Lowry bases. So we're asked to write the formula for the conjugate acid. So the bases accept hydrogen. So we're going to add one hydrogen to the formula, and we're going to add 1 to the charge. So my formula is SO3 2 minus. If it gains a hydrogen, it becomes HSO3. My original charge was -2. We're going to add 1, so the new charge is -1. So my conjugate acid is HSO3 minus. And then finally, we've got a CH3, 2, and H. We are adding a hydrogen. It matters where we add that hydrogen. So it matters where the hydrogen is placed. We're not going to put it on the carbon. First of all, the carbon is full. Remember, carbon can only form 4 bonds. It's got 3 bonds to hydrogen. Its 4th bond is to the nitrogen. We're going to add it to the nitrogen always. So this is going to become CH3, 2, and my hydrogen goes up by 1, so it becomes NH2. We start with 0 charge. We're adding 1 to it, so its charge is now +1. So my conjugate acid is going to be the CH3, 2, NH2. So we mentioned earlier that we need to be able to write proton transfer equations. So that's showing what happens when we put our particular acid or base into water and having it form its conjugate acid or conjugate base. So we're going back to problem 14. So we had HSO4, and we said that it was an acid. So if it's an acid, when we put it into water, that means water has to be what's accepting the hydrogen. So the HSO4 minus is giving the hydrogens away. Water's got to be accepting it, so that's got to be the base. We've already identified the formula for the conjugate base. We said it was going to be SO4 2 minus. So during this process, the HSO4 gives a hydrogen to the water. If we're giving a hydrogen to water, water's hydrogen is going up by 1, so it becomes H3O, and then it's going to be a plus. If I identified what I put into water as being an acid, then we have to be producing hydronium. That is one of our other definitions of our acids. So this would be our proton transfer equation. It's showing the HSO4 minus giving a hydrogen to the water to form the conjugate base SO4 2 minus and the conjugate acid H3O plus. Then we had CH3 and H3 plus. We said that was our acid. So again, that means water must be behaving as the base. So we put that into water. We're going to transfer hydrogen from the CH3 and H3 plus to the water. We said that our conjugate base was going to be a CH3 and H2. The hydrogen leaves that NH3 plus area. It transfers to the water. So the water becomes H3O plus. And then finally we had our HF as our acid. We put that into water. Water is the base. We give the hydrogen to the water, leaving behind F minus as our conjugate base, and H3O plus as our conjugate acid. So again, all of these were identified as acids initially. All of them are producing hydronium. They're doing so by donating a hydrogen from the acid to the water. And then for our bases, we had the SO3 2 minus, so that's our base. We put it into water. So this time, the SO3 2 minus has to accept hydrogens. It has to gain hydrogens. It's going to take the hydrogens from the water. So water will be an acid. Water will donate a hydrogen to that base, forming our conjugate acid. And then if water is giving a hydrogen away, it goes down by 1, giving me OH minus. And then finally, we've got our CH3, 2, and H, we said was our base, which means water will be the acid. Water will give a hydrogen to that base. So our hydrogen goes up by 1. We're getting our CH3, 2, and H plus, which we said was our conjugate acid. And we're getting hydroxide, so water goes down by 1 hydrogen and leaves behind OH as our conjugate base. So we're going to become very familiar in this chapter with writing these proton transfer equations. Anything we do acid-base wise, we've got to start with the picture of what's happening. We put that acid or base into water. We're going to either donate a hydrogen to the water and form hydronium in the case of an acid, or we're going to take a hydrogen from the water to form hydroxide if it is a base.